हेलो हेलो, आवाज आ रही है? So students, today we will discuss Newton's law of motion. Actually, yesterday the same class was there, but due to some technical problem, the voice was not clear. It was reported by some students that voice is not clear. Therefore, I am again giving lecture in this class. The same thing which I delivered, the lecture which I delivered yesterday, the same thing I will again repeat it. So, this is chapter 5 in H.C. Verma's book, that is Newton's laws of motion. Right? These are very famous law. You know that there are two types of set of rules. One is classical, one is applicable in the classical physics, which we observe in our day-to-day life. Another one is quantum physics. A lot of many laws of physics are not working, not holding true in this quantum physics. This is not our point of discussion today. Just I mentioned what is classical physics and what is other than classical physics. That is quantum physics. So what I want to emphasize here is that Newton's laws are very important laws in classical physics, or most of the phenomenon which we observe in our day-to-day life, and a large number of section of this book which deals with the classical physics. Two things are there. Classical physics and quantum physics is not our point of concern here. I just mentioned that sometimes it is written that Newton's law of motion are of central importance in classical physics. That's why I mentioned here. So one thing is, in this chapter we will deal with force. And whenever force is there, some acceleration will also be there. Moreover, where we will apply the force, or if any force is applied, where it will be applied. It will be applied on any object that object will be having some mass. So force, acceleration, mass will be the main features of this chapter. And whenever there is acceleration, there will be some velocity there will be some displacement, there will be some speed, there will be some change of location. So all these things are interconnected or interrelated, right? Here in this chapter, we will mainly discuss the nature of force, and we will try to find what sort of force is being applied or being felt at various bodies. In one body having some mass, there may be one or more forces being applied or being felt simultaneously. There may be 1, 2, 3, or more also. Okay. This is the main point of discussion of this chapter, right? Now, one concept is that a very important concept is frame of reference. Frame of reference. What is frame of reference? A setup. Not necessarily created, it may be natural. A surrounding. Surroundings of an event. Where some force is applied on some object. Suppose I am standing here and trying to kick a football. And this is not a classroom or lecture theater. It is simply a playing field. And I am standing here running, jogging, walking, anything I am doing. I am not stable. I am doing some exercise or playing some game. And I am here and I am kicking one ball. I am applying force on that ball. So that field where ball is present, I am present, and that field is present. That is called surrounding, setup, or frame of reference. Likewise, there may be different frames of reference. Very commonly used example is a boy sitting in a compartment of a moving vehicle, or say train. So the boy is sitting in a compartment on some seat and playing the ball. Another man is standing here on the platform and train is moving like this. So the frame of reference is different for different persons. One person is sitting on the platform, one boy or one person is sitting in the compartment of moving train. And this boy is tossing the ball, throwing it upwards, and then again when it comes down, taking in his hand, grabbing in the hand. Very simple game. Almost all of us have played, like throwing ball and catching it again. Throwing ball up, then catching it again. Throwing ball up and catching it again. It's a simple game. For this boy, with respect to compartment of train, seats in train, with respect to other fellow passengers in train compartment, this boy is not moving, is having a constant position, not moving, still position. They may feel that the things outside the compartment are moving backward, like agriculture field and trees and electric poles and other people outside on the field and road and village and city, etc. They are moving backwards for them. But for them, this boy and the seat and the compartment, etc. are in still position, and only thing moving is the ball which boy is throwing up and then taking it again in its hand. So this is the one frame of reference. But for the person who is sitting in the, who is located in the platform, the train is coming and going zing, and the boy is also moving with the speed of train, right? What will be the trajectory of ball as observed by this person who is sitting on the, who is staying on the platform? For the boy sitting in the train, the trajectory of ball will be like this, going up, coming down, going up, coming down. Same vertical line repeated many times, so many times. But for the person, the ball will go up, come down, again go up and come down, again going up and coming down, again going up and coming down, till he can observe. After some time, it will be out of sight, for the observer standing still on the platform. So the same phenomena is being observed by two observers in two different frames to be different. Its trajectories are different, its velocity is different, and in this case, there is no horizontal component of velocity of ball, and in this case, there will be a horizontal component and there will be a vertical component of the movement of the ball. So this is the difference of frames of reference. So in any case where we are going to study the force, that should be, the frame should be well defined, and that is called inertial frame of reference. Another thing that I would like to add here, inertial frames of reference are those frames where Newton's laws hold good. There may be some non-inertial frames. Where this Newton's law or the events occurring in this frame does not follow or does not obey the Newton's law of motion. They may be governed by some other set of rules. In that frame, they may not be doing they may not be giving the result as per the Newton's law of motion. So in that case, we have to follow some other rules, right? Now, come to here it is very important, and for your information and general broader perspective, I would like to give another example for the frame of reference, because nowadays a lot of space expeditions are going on. Recently, almost all of us has watched the Chandrayaan, in which Indian Space Research Organization has sent a space vehicle to the moon, and this is still in the way to the moon. So, in this 21st century, we are living in the space expeditions age. And every one of my students have heard about space stations. Space stations are stations which are located few hundred or few thousand kilometers above the space, and few astronauts are living there for a long period of time, and they are doing some specified research work there, but still they find time to observe our Earth from their space station, right? So suppose here on the Earth, I and some of you, maybe 10, 20 or more, somewhere on the Earth in a football field, we are playing a game of football. So for us, this is the flat surface as far as a human can see. The globe is flat for us, and in the field we are playing football game, and we are running in that particular field randomly, here to here, here to here, there and there and there. Within seconds, I am here. After 10 seconds, I will be there. Right? Like any player. And for us, this Earth is constant. Only I, other players, and ball is moving. Right? But for a person sitting on the Earth, having a very fine telescope, and they are watching us through their telescope, they are watching us playing football. For them, how it will look like? There will be a circular motion also, in addition to our random linear motion, right? So, why it is so? Both are sitting in different frames of reference. And in future, or maybe 25 or 50 years from now, this scenario is very common. Suppose I am sitting here, you are sitting here, someone is sitting in another space station, someone is sitting on the moon, staying there for a long period, and when we will start talking, then one has to specify its frame of reference, from where they are observing or talking or speaking something, or sending signals. Then and only then a compatibility will be achieved. Otherwise, he will say, no, you are not only playing, you are also doing a circular motion. Then he has to specify from here he is watching us playing. Right? Now, let's move on to the first law of motion. So, frame of reference is clear to everyone? To everyone, frame of reference is clear, I hope. If you have any question, you can write it down in the comment section of the app. Right? आवाज सही है? Now, the first law of motion. If on any particle, here particle means a point mass or if an extended mass, point mass is like this, or an extended mass or a mass having extended body like football or any stone, say, right? Say any stone. So in an extended body mass, it is supposed that its whole mass is concentrated in a point where its geometrical center or center of mass is situated. This is the point here. So when we are talking about the particle mass, it doesn't mean when we are talking about a particle on which some force is acting, it doesn't mean that a very small particle, there is a force acting. Practically, it is not possible that you apply a force on a particle. So it is supposed that the mass is concentrated on the center of gravity or center of the mass of some extended body mass. That's clear. So what the first law of Newton's first law is telling is if on any particle there may be more than one forces acting on it. So we have to take the vector sum, right? The vector sum means you might have studied vector addition. In fact, vector addition and vector subtraction are there. And we have discussed it at length in our previous lecture. So it is telling the vector sum of all the forces acting on a particle. If it is zero, if the vector sum of all the forces on a particle, suppose one particle is there and force is there acting on it, also this force is there, and opposite forces cancel each other. This force are equal and opposite, may be equal, opposite is there. This is force having not a counterpart, just opposite to it, but its component may be resolved to this direction and this direction, and the resultant of all the forces is zero. Right? There are 5 forces, not necessary that they are equal and opposite. Some force may be not having an exact opposite counterpart, but its factors, it may be factorized in different directions, x-axis and y-axis, and it is balanced by the other forces. But the resultant sum of them is zero. In that case, particle will remain in rest or in constant motion with which it was moving before the application of force. A particle is moving in constant motion and have come here, and here suddenly it feels 4 or 5 forces, but their resultant sum is zero. Resultant vector is zero. It will remain moving in the same direction with the same speed. Or if it is not moving, it is being in rest with particular frame of reference. And suddenly it feels a lot of forces, 3, 2, 4, 5, 6, 7, 4 suddenly working on it, and the vector sum of them is zero. Then it will remain in rest. What does it imply? That to move in any particular direction, depending on the direction of force, the particle should have a non-zero force applied on it. The vector sum should be non-zero so that it will start giving some result of that applied force. And what is the result? It will start moving with a acceleration. What is acceleration? It is velocity varying, increasing velocity, right? One very commonly used example and very useful example is given in this book, that is falling elevator cabin, right? One elevator cabin is there, one person is sitting there, standing there, one massive object is there, held by a string, and one, you all know that elevator cabin is held securely and tightly with a thick rope. Suddenly, and one person is standing here on the ground. Suddenly, this rope breaks. Then what will happen? This elevator cabin will start coming down with the acceleration. What will be the magnitude of acceleration? That is g, which we know it is 9.8 meters per second square. In this frame of reference, they may feel that they are also coming down with this acceleration. But when the person who is in this cabin, he will watch this, he may feel that this body or this object is in rest with his position. It is not moving. But for this observer, both are moving down. So, if the before breaking down, it is coming down or going up with a constant speed, and in this if this body is there, suppose it's a body having mass m, and due to m it is having a weight. What is weight? M into g, and it is balanced by this rope, this string. This string is applying an equal and opposite force to that of this weight, so that it is held securely and is in rest inside this cabin. In that case, the weight will be equal to tension or tensile force applied by this string. Even if it is falling, this observer, this person situated inside this elevator cabin, will find that the same equation will be true. Correct? Okay. So but for this person, this is coming down. Each and every part of cabin is coming down with the acceleration, that is g, right? Now let's move on to the another example. One table is there. And it is resting on the floor. Another object having some mass is resting on that table. Do you think is there any force working on these two objects? Normally, we say no, there is no force. There is no force. And this is the fact also that there is no force. But fact is that there is a force because Earth is there and 24 hours every second it is attracting everything which comes in its influence. Means all objects on the surface of Earth are attracted by the gravitational force of Earth. That's why things are stable here. So this table is feeling an force of attraction towards the Earth. That's why it is stable on that. It is resting stable on that place, that room, or that surface, or that floor. And this book also is feeling the Earth attraction force. And that's why it is resting on this table. But what is there? If only one-sided force is applied, then the sum of force will be non-zero, and the object will start moving like an object falling freely under the influence of Earth's gravitational force. Some fruit falling from the tree and coming down on the head of the Newton. In that object falling freely, there is only one force, that is Earth's gravitational force. There is also gravitational force being applied. Then why it is not falling? Because this surface, this floor, and on this book, the surface of this table, top of the table, is applying a equal and opposite contact force. Right? There is like this pen, now it is falling from this height, and it is under only one force. But when it comes on this table, equal and opposite contact force is applied by this table, like this. When it comes in my hand, this surface of the hand has started applying a equal and opposite contact force on this. Right? Or you can consider a ball. You can consider a ball. Suppose a ball is there attached with a string of length 10 meters. Right? This distance is 10 meters. But here it is attached with a hook through a string whose length maybe not 10 meters, you can say 9 meters. And suddenly you throw this ball so that it will start coming down under the influence of gravity, and there will be a free fall. So it will start coming down. But as soon as it comes to the distance of 9 meters, the string attached to it will apply a opposite tensile force. Opposite to what? Opposite to the gravitational force. And then it will remain in rest or still. Then it will stop coming down. Right? So at that point of time, it is under influence of two opposite force, or the vector sum of two opposite forces are zero. Vector sum of two opposite forces are zero. That's why it is not moving now. Although it is feeling two forces, but it is not moving anywhere. Right? That's what it is being told in the first law of motion. Right? There are some more examples are there in the book that you can go through, and again we will discuss this if something arises or some questions comes from your side. Right? Now let's move on to the second law of motion. Second law of motion states that the acceleration of the particle, you know that force and acceleration are very intimately related to each other. Force is proportional to acceleration, or acceleration is said to be proportional to the force. This will be much better expression, that the acceleration is proportional to the force. जितना फोर्स अप्लाई करोगे उतने रेशियो में एक्सेलरेशन आएगा. But they may not be equal. There is no equality sign. There is only proportionality sign. To have one equality, some more equality constant has to be there, so that we can convert the proportionality sign into equality sign, right? And here comes the value of mass, not weight. Because mass is an universal unit and weight is a conditional unit. Whenever a body is feeling the gravitational force of Earth, then its mass will be expressed in the unit of its weight. Everybody knows it. Whenever we go to the market and the fruit seller or vegetable seller weighs something, it is weight only, not mass, right? And you can convert weight into mass with the help of this factor. Applying or dividing this factor, that will be a conversion factor of mass and weight, right? So, the second law of motion, the statement is, in any inertial frame, the acceleration of a particle is given by the vector sum of all the forces, or you can say resultant force. Simply, instead of saying vector sum of all forces, we can say resultant force. Smaller term. So, the acceleration of particle in an inertial frame of reference is equal to, acceleration is equal to the resultant force divided by its mass. And this is the one of the basic principles of physics. Later on, you will study the momentum, and few other terminologies, few other terms, but this equation holds true in every situation. At some time, in some examples, the mass is replaced by the momentum, not exactly replaced, but it is suitably substituted, adding its velocity also. Mass and momentum are not same, but in some equations, in quantum physics, the momentum is used in place of mass. That we will study later. But this equation, A is equal to F upon M, is a universal equation. That is second law of motion. That acceleration is proportional to mass, and when proportionality is to be changed in equality, then force has to be divided by the mass. Or in another words, you can say F is equal to MA. This is the very famous equation and very useful one, and it has a universal application, means it can be applied in any situation. But the thing is, in every case where we are applying this force is equal to mass into acceleration, the basic condition is what is the basic condition is The frame of reference should be inertial. Means the observer, the object, and the force should be in a same frame of reference. Right? So, with this, I am concluding today's class. And tomorrow, we will analyze some examples giving a detailed analysis of any force acting and what is the direction and what is the nature and what is the magnitude of force. There are 2-3 more examples are there where you can or any student can study or understand the nature of force. Right? So, with this statement of second law of motion, I am concluding this class, and tomorrow at the same time we will again come to the class. I will again come to live and I will try to explain the rest of the examples in this chapter. With this, goodbye for today. We'll see you tomorrow.